Hi everyone, I'm Akanksha Kar and my teammate Varun Jain. We want to discuss our visual learning and recognition project, which is about robust photorealistic VR facial animation via multi-view image translation. This will be the outline of our presentation, so let's dive into the problem statement. This pipeline in Figure 1 aims to build photorealistic 3D face avatars from high quality Capture Studio data and the limited sensors mounted on the VR headset to make two-way social interactions in VR believable. The problem is this that the headset mounted camera placements tend to provide only partial and non overlapping views and at extreme and oblique views in IR spectrum. The system with 9 captures can find correspondences to give good and realistic expressions, but during inference, we only have 3 views and no correspondences. This system is also not robust to variation of input caused by factors such as different camera positions, different VR headsets, and illumination changes. Any such changes creates a lot of problem for our system to predict correct avatar. As we can see, there is a huge mismatch in the predicted and the correct expression. So let's see the methodology which we want to use to solve. This is our pipeline for this project, and we are trying to pass the UV coordinate maps to the avatar generator module. We believe that the best way to solve mentioned issues would be to bring these IR images with various expressions and any headset variation into a standard canonical form, which we call UV coordinate map. Here we are using a unit type architecture for fully convolutional neural network to predict UV map in real time and feed to our avatar generator to predict correct expression.
Okay, so now I'll give an introduction to what UV coordinate maps are and how they may be of help. A UV coordinate map gives us some sense of the underlying 3D geometry associated with a given 2D image. As we can see in the figure, what we have as the input is a 2D image, and there is no explicit information about the geometry associated with this face. However, if you look at the far right, the 2D image gives us some idea of, for example, how the presence of the nose in the middle of the face changes the otherwise smooth gradient in the image from left to right and top to bottom. So hypothetically, if the geometry of the face were flat, the image would have absolutely smooth transitions in colors in all directions. In a nutshell, it is a way to convert the underlying 2D input to a canonical texture space, which is largely unaffected by the camera pose and extreme expressions. More importantly, the topology of these maps remains the same for all identities, so it may be helpful in building a universal encoder-decoder that works for all people. And this would become more clear as we see how we generate these UV maps. Here, all the things in the red boxes are the input and the ones in the green boxes are the output. The SIGGRAPH paper proposed a sophisticated system that takes in NIR images from 9 views, puts it into an encoder-decoder network, which gives us a predicted 3D mesh of the face. The decoder works very well if the input at inference closely resembles the training distribution in terms of the identity of the person and their expression, appearance, and illumination. And we make use of this fact to generate high quality 3D meshes. Another thing that they have is a renderer that, given an input 2D texture along with the mesh and the camera parameters, renders the texture onto a mesh. It also predicts a mask. Now we replace the two textures by two lens spaces in X and Y directions and render them onto the known geometries. These come out as the V and U coordinate maps. The value of both of them is constrained between -1 and 1. And as you can see in the output, the V coordinate map gives us some sense of the change in depth as we move along the y-axis and cross the lip region. Now we look at some results. On the first column, we have the V coordinate map, followed by the U coordinate map, and then a visualization of the combined map. The lines correspond to the isocontours of V and U coordinates. These deformed isocontours give us a very good intuitive sense of the geometry. Okay, so to predict these UV coordinate maps, given just a few NIR images from different views, we use a unit style network to jointly predict V and U coordinate maps. The input is a 2D NIR image from a single view, and the loss here is a per pixel root mean square error, and we train it approximately on 5,000 image pairs. Here are our results. The isocontours in the case of mouth are very clean, and we can see that it captures the geometry of the nostrils and mouth quite nicely. However, since the eye portion is a lot more complex, the results here are not that great. A point to note here is that the V map is especially bad since the changes along the X direction along the eye region are more gradual and continuous.
So let's see some results of the overall pipeline. Here are the quantitative results. These are the inference time losses for 70 peak expressions where the model is not performing up to the mark. The dark blue line is for our for the input is IR images for the avatar generator module, and the red and the light blue lines are for input as UV maps only using predicted or ground truth UV map respectively. We can see that the UV maps are helping considerably in reducing the geometry loss, the camera rotation and translation loss. This helps in getting better performances, as can be seen in next slide. Here we see the qualitative results, which finally show the importance of UV maps. We can see that even though the results do not completely solve the problem, but they are in the correct direction to help solve the problem.
As a closing remark, we would like to explore the following avenues to help solve the current problems in UV map generation. First is the inclusion of key points. It might be helpful to detect key points on the face image and then align this 2D image to a 3D morphable model of the face. However, the problem here is that robust key point detection in NIR is not trivial. Also, we do not have the whole face image, but only 3 disjoint parts of it. Next, the current loss function is a pixel-wise root mean square error, so it is totally unconstrained. However, we can put some really strong constraints on the values of V and U coordinates since they should not change drastically over a local neighborhood. Lastly, the current model that we use has very sparse geometry in the face region, and hence there's a huge loss of detail there. So we can explore alternate ways to generate the reference input data. Thank you.